So the lithosphere is broken into about 24 segments of irregular size and shape called lithospheric plates, or just plates. They're in constant motion with each other, and you can see them outlined in the image to the right, which is the same image that your book has. So there are 7 major plates that account for about 94% of Earth's surface, and those are going to be, let me see if I can figure this out. They're going to be the North American plate, the South American plate, the African plate, the Eurasian plate, Pacific plate, Australian Indian plate, and the Antarctic plate. The largest one of those is the Pacific plate, which accounts for most of the Pacific Ocean basin. The other 6 that are there outlined encompass a specific continent along with significant amounts of oceanic crust as well, such as you see in South American plate, for example. There are also intermediate sized plates, which include the Juan de Fuca plate, which is not labeled in that diagram, but it's pretty much where I'm showing right there, just west of the North American plate, a tiny plate there. You also have the Caribbean plate, the Cocos plate, the Nazca plate, the Scotia plate, the Arabian plate, and the Philippines plate. So these plates, with the Arabian plate being the exception, are mostly composed of oceanic crust. So all of them except the Arabian plate, for the most part, occupy only oceanic crust. So plates move as somewhat rigid units relative to all other plates. So as one plate moves, the distances between 2 geographic locations, if they are in different plates, will change. However, parts of some plates are comparatively weak, such as parts of southern China, for example, which are being squeezed as the Indian subcontinent is ramming into Asia proper. Because plates are in constant motion relative to each other, most major interactions occur along their boundaries. And in fact, the boundaries of plates were initially mapped based on seismic and volcanic activity, which are both signs of plate boundary interaction. So that you can see in this image below. You see that for the most part, these earthquake and volcanic activity that is going on outlines pretty well the different boundaries where the plates are currently delineated based on this upper map as well, right? So based on that, there are 3 types of boundaries that are possible. Divergent being the first one, and this is where plates move away from each other. Convergent, where plates move towards one another. And transform, where they slide or they grind past one another. So again, given this map, which you will see again in each of the following slides, the divergent plate boundary is the red delineations that you're seeing, these boundaries between them. The convergent is the blue, and then the transform is the green. So that will become important once we talk about different examples. So in the following slides, we'll go over the 3 types of plate boundaries, their nature, where they occur in the globe, and whether they are responsible for either creating, destroying crust, or for neither. So the first plate boundary type we'll look at are divergent plate boundaries. So divergent plate boundaries occur when 2 plates are moving away from each other. Di comes from the word apart and verge from the word move. So they're moving apart. So this is kind of the motion that they have. Great. So about 40% of all plate boundaries, are on Earth are of this kind, of divergent plate boundary kind. They are typically located on the crest of oceanic ridges, and you can think of them as constructive plate margins because this is where new crust is being generated, typically in the form of ocean crust, which is in the ocean floor where the oceanic ridges are. This new crust is made when 2 plates move away from each other, producing a long and narrow fracture in the oceanic crust. As a result, this hot molten rock from the mantle below moves upward to fill the space that is left as the crust is being ripped apart. Also, this hot mantle is less dense, so it wants to rise upward. That's the reason it does it, because there's space now available, and because it is less dense, so it wants to rise upwards and be more buoyant. So slowly, this molten material cools to produce new slivers in the ocean floor. So, let me see. So this short example kind of represents how that works. So imagine that you're looking at the page as a map view, meaning from above, and that the new crust is coming from depth, so within your screen, okay? And coming to appear on your screen as it rises to the surface. So the red rectangles that you're seeing here represent the newest crust rising from below, and as they get closer to green, it gets older, okay? So let's see. So now you see that those initial red rectangles displace themselves towards the sides, and new material, which is the new red rectangles, moved upwards and further upwards and further upwards. So that's kind of the idea of how this occurs. At, again, ocean ridges. This is where this occurs. Let me see. Okay. So you see here again that the crust is getting older as it gets further away from the ocean ridge, or the spreading center, which is another way which we call this. So because of this specific process that is taking place here, the process that causes new crust formation is called seafloor spreading or rifting, okay? Usually seafloor spreading because it happens at ocean basins, but every now and then it does happen near continental land masses, so it's rifting apart the two different land masses, and that's why we call it that way. The oceanic ridges are elevated areas of the seafloor where there is new crust being formed, as we said in the last slide, and where there is high heat and volcanism taking place usually. So the overall oceanic ridge system, which comprises all of the spreading centers, is over 70,000 kilometers long, which makes it the longest topographic feature on Earth, which is pretty cool. These ridge systems tend to vary in width from 1,000 to 4,000 kilometers, but the crest is only about 2 to 3 kilometers in width. Along the crest of some of these ridge systems is a deep canyon-like structure called the Rift Valley, as you're seeing in the picture. And it is a feature that gives evidence to the tensional forces at hand that are pulling the crust apart. You can see that Rift Valley in Iceland, for example, as is shown in the picture on the lower part of your screen. There is the Mid-Atlantic spreading center that goes right through Iceland, and you see in the picture the canyon-like structure and the apparent pulling apart of the already existing crust, right? So the average spreading rates are of about 50 millimeters per year, which is about the same rate at which our fingernails grow. But this rate varies depending on the segment that you're looking. For example, the Mid-Atlantic is only about 20 millimeters per year, but rather the East Pacific Rise, which is another section of the ocean ridge, in some sections is spreading as fast as 150 millimeters per year. So again, some parts of the Mid-Atlantic Ridge, 20 millimeters, some parts of the East Pacific Rise, 150 millimeters per year. So very different rates of spreading. So I know that these rates seem kind of slow in human timescale. In truth, 150 millimeters is not very much per year. But they are very fast enough indeed to have created all of the oceanic crust in the last 200 million years or so. If you guys remember from some of the evidence for plate tectonics we saw, or some of the evidence that was found, some of the discoveries that were found, was that oceanic crust was younger than 180 million years old. So this rate of spreading must have been fast enough for all of the oceanic crust to be created in the last 200 million years or so. So the reason that we see a ridge is because the new crust is hot and hence less dense or buoyant, in comparison to the pre-existing crust. And because it is of this nature, it is less dense or more buoyant, it wants to rise to elevations that are above it. So when the new material is formed and placed, it is slowly displaced away from the zone of mantle upwelling, and hence it begins to cool and to contract, which makes it increase in density and sink back down a bit, lowering its elevation. So this process takes about 80 million years total, and it is sort of what you're able to see in the picture above. So you see the ridge system being a little bit higher in elevation than the things to the sides, because again, it's hot, buoyant, and less dense as it's close to the ridge, and it gets cooler and denser, and it starts to sink back down as you get further away from the ridge. Okay? So in addition, as the plate moves away from the ridge, cooling of the underlying asthenosphere causes its upper layers to become increasingly rigid. So the older the new formed lithosphere gets, the thicker it gets as well, because it is adding material at the bottom of this lithosphere by the cooling that is occurring at the top. So as the lithosphere that gets away further from the ridge begins to cool, it also starts to cool parts of the underlying asthenosphere. As it cools these parts of the underlying asthenosphere, the asthenosphere starts to add a little bit of that material that is now being cooled. So because it's being cooled above, right, further away from the ridge in the lithosphere, it cools parts of the upper asthenosphere and hence adds material to it. So the further away from the ridge, the cooler it gets, and also the thicker it gets. Okay, so although most spreading centers occur in the seafloor, as we saw in the previous slide, we also have new crusts formed in the continents, occasionally by these divergent plate boundaries. These areas are called rift zones, where you have continental rifting or spreading of continental land masses. Those rift zones, however, almost always cause the creation of a new sea, as shown in the diagram in the screen. So you're seeing there is rifting going on between Africa and the Arabian Peninsula, those two plates, the African plate and the Arabian plate. And so you're seeing that because of this rifting is taking place, the Red Sea is appearing, and you see that as rifting continues to occur, the Horn of Africa is fully going to detach, and there's going to be a sea kind of engulfing that whole area where, for example, Lake Victoria kind of lies. Lake Victoria is eventually going to merge into the coming sea. So again, that's a good example of the current rift zone that is going on, and this particular example is called the East Africa Rift Zone. And again, it is caused by the spreading of the Red Sea in this case. I really like the diagram that I put here on your left, and it kind of explains this continental rifting really well. So if you need to pause the video and read over what the diagram has to say for each of the time steps, I encourage you to do so. And it kind of shows very well how this rifting of two continental land masses turns out to be, in the long run, a mid-ocean ridge like we see, for example, in the Atlantic today.